Hi everyone. Hi. Thank you for taking some time with us to learn about the wonderful and wondrous world of kernel crashes and all of that stuff. We'll be mainly talking about crashes, how to debug these crashes, and also take a sneak peek at how performance can also impact all of this. So this talk is mainly aimed at being an introduction to all of this. The main goal here isn't to cover all of the possible crashes or anything, otherwise it would likely take ages. But it's more of, its goal is more to help you have pointers and good practices when you encounter some of these crashes to get an idea of how to debug them and what to look for and all of that kind of stuff. So my name is Ballasi. Thank you for listening to me. I will be presenting this talk with Hardik Garg, which is here. We're both Microsoft employees working as part of Linux Systems Group, where we mostly maintain some of the Azure Linux products. So Azure Linux, Azure Boost, that kind of stuff. Okay, so let's go ahead. And the way that this talk has been split is considering the fact that we consider there's 3 stages of a kernel breakage. The first one is that the kernel itself would work just fine. There is no issue at all, so this is something we'll skip because it's obviously the kernel we want to achieve. The second one is one where we see kernel crashes, kernel panics. So when we'll be talking about that, we'll go over a few examples. We'll go over how to debug these examples, and basically, as I said, see all of the good pointers and what to look for when taking a look at that. But finally, other than having a kernel that works and a kernel that crashes, we can also end up in a kernel where the system works for the most part, but we can see a lot of performance issue on that end. So we will see on the second part how command line parameters can have an impact on performance. So we'll see these kernel parameters and see how this handles with security vulnerabilities and mitigations. So as I said, let's start with kernel crashes. We'll go over this by looking at a few examples and seeing how everything, like how we'll work this out. The first example we'll be given is a very simple and concrete one. It's one of a Stack Overflow. So the idea of a Stack Overflow, you might know it. It's the idea that somewhere in our code there is a deep or infinite recursion happening. This happens when the program uses way too much memory on the call stack, which would lead to a crash when the memory stack limit is being exceeded. Let's take a look at a sample example code. We'll mostly go over through kernel modules there, because it's the easiest way to understand it. So basically here we have a kernel module that inits and call a function called recurse with a value of 1, and that function, as you can see, is just calling itself on loop, on loop, on loop. One thing that could be interesting to look at here is there's a reason why we added a value to this function and why we increment this value. It's obviously to the idea that if we want to have a code fix to it, we can use that value to set a hard limit on what would be the maximum recursion limit. Say, if we reach a certain point, like 50 recursion, we'll return an error, or we'll try to handle the situation in any other ways. That depends really on what you're trying to work in. Say, for instance, if you're working on networking and you're trying to achieve to get to a network that's unavailable, at some point the recursion will want to just stop and do something else. So what happens when we run this code in our Linux kernel? This is what we see on the kernel ring buffer. So usually when I take a look at the kernel ring buffer and dmesg, there's 2 main things that I'm trying to look out for. The first one is understanding why the issue is happening, and the second one is understanding when the issue is happening. So luckily for this example, since it's something that the kernel catches pretty easily, it's very simple to understand why and when. Just the very first line after loading the kernel module, we can see that there is the stack protector being called that say, hey, there's something with the kernel stack that is being corrupted in this function. So the function here is trigger stack overflow. It's our recurse function that I just renamed for easier understanding. But yeah, basically here there's already the kernel saying, hey, there's something happening with the stack. Why is the issue happening? Because of the stack. And somewhere in trigger stack overflow in our recurse function. This one is pretty explicit, but usually when I try to look for when the issue is happening, I really like to look at the call trace. In that example, it also gives us more data about where it's happening, because it also tells that it's happening inside our Stack Overflow module. So in that case, it's pretty easy to understand what's happening and what's the change to do, but let's take a deeper look at how we can actually debug this issue and how we can find out exactly what happens using two different debugging techniques. The first one being KASAN and the second one being GDB. So let's start with KASAN. KASAN is a tool that has been included inside the kernel by version 4. The goal of KASAN is basically to have some dynamic memory error detection inside the kernel for instance, use after free out-of-bound bugs, but in more general way, in every memory issue that we can end up in. The way it works is that it uses compile time instrumentation to check each memory access. You will see that if you enable it on your system, it will allocate 1/8 of the heap memory just for himself, just so that it can take a look, it has a shadow of what's happening exactly inside the kernel. The way to get it installed in your kernel is pretty easy. It's just a few command line parameters, a few configs, sorry. Basically, KASAN is the main one. We also enable KASAN inline for that example, just because it will print out all of the KASAN outputs to the ring buffer. And once we give our example a try with KASAN, after recompiling and booting the new kernel, this is what we get. So we have a much deeper log about what's happening. This time, the kernel doesn't just say, hey, there's something happening with the stack. Now it really says there is a stack out of bound. We're going out of the stack in our function that's happening inside our module. There's also logs about the call trace happening here. And KASAN also gives us some more information about the memory itself. All we can see now is that it reached to a point where basically it's out of memory. Now that we've taken a look at KASAN and got an actual out-of-bound errors, let's take a look at GDB and how we can use it to debug our kernel. So GDB is the GNU debugger. It's something that we can use runtime inside the kernel to do, for instance, breaks in it and modify values, print out registers and everything. So in our case, we just target remote to our kernel. And as I said, we can use breakpoints. Here I've given an example of breaking on start kernel, but we can, in most of my examples, I will mostly break on the init function of our module, because we know that the module is at the cause of the issue. And after that, we can continue running the kernel, doing steps, everything, and we can also print the backtrace. So in the example that I've done below, what I've done here is that I've braked to our module, and I've done some few steps. And by doing some steps, I've seen that, hey, I'm going on recurse on loop, on loop, on loop. And by printing out the backtrace, we can see that the recurse function is being called multiple times. Using GDB is very important in some few cases of testing out the kernel, because here it's pretty clear that the issue is coming from our module, but there can be some cases where there is some part of the kernel that causes an issue that would still work, but would feed any input that is wrong to another part of the kernel or another module that itself would fail. GDB is a good way to understand basically the root cause of the issue. So now that we've had knowledge about KASAN and GDB, let's take a look at another example and how we can use it to debug this issue. This issue being use after free. which is the idea that we're trying to use a pointer after it's being freed. It's something that's very important as part of the kernel, and memory-related issues is very important in the kernel, but especially this one because it can lead to arbitrary code execution and other than crashes and everything. And it can be very common with race condition coming from threads or that kind of stuff. So it's really something to look out for. Here's a simple example of a use after free where we malloc a certain part of our memory, we free it, and we try to print the data. What's interesting in there is that even if we run this code, there can be cases where it actually works just because it points to a part of the memory where there is data. On my side, when I've been trying it, most of the time it would work and it would just give out garbage data that's not usable. Hopefully, KASAN is there for the win, and it detects by default that there is a use after free coming in our kernel in basically the init module of use after free. So KASAN is a very important memory-related tool. If you see anything happening weirdly with memory in your kernel, enabling KASAN would be a very first good step to do. Let's take a look at now how we can use GDB to debug this. In that case, we actually end up having a segmentation fault because we're reaching a part of the memory that we're not using. And by using backtrace, we can see that the segmentation fault is happening at the init function of our module. And reading the registers, we can see that at the time of the crash, a register holding pointer may be invalid or point to some part of freed memory region. We can always print out some values in GDB if we need to inspect. As I've said, this is a very important issue that's like a very serious vulnerability to look out for, and that could lead to a lot of crashes. So it's very important to know how to circumvent this issue. What we do is that whenever we free the pointer, we usually set it to null so that we can track which pointer is still existing and which pointer is still not existing, so that whenever we try to use that pointer, we can use, as you can see here on the second line, we can test out if that pointer is null or not, and if it is null, we can just return an error saying the memory is not defined. It's very important to do that because if we don't, it's going to lead to a null pointer dereference, which is what happens when you try to access a part of the memory where it's null, where it's 0, where it could be uninitialized, for instance. This causes a crash, obviously, because it tries to read a part of the memory that cannot be read or written. And here's a very simple example of that. So we're having a pointer that we set to null that is static, and we're trying to write a value to it. And when we try to run that, we end up on a crash. So here we can see that the kernel notices that we're trying to access the memory at address 0 and say, hey, you're having a null pointer dereference. We can see that there is a PF on the next lines. This means page fault. There is something happening when reading the page. And later on with the memory, we can also see that some of the registers say RIX are equal to 0, which will lead us to the point that we're trying to access a part of memory that is a pointer to null to 0. And to the question of when this is happening, we can see that there is a null the instruction pointer, the RIP is pointing to null pointer deref init, which would give us the hint that this is where the issue is happening. With KASAN, it gives out all of the information that we need, as always. It says, hey, you have a null pointer dereference happening in range 0x000. Here are all of the memory, just like the kernel says. And when we're trying to use GDB, in that case, when we're looking at the backtrace, we can see that also the page fault is happening at an assembler level. So if you look at the very bottom, it says ASM exec page fault. And one thing I like to do in that case is also to take a look at the disassemble to the assembly of the function, where we can see a moveL function of 0x to a, so that's 42, the data that was in our function, to the address 0x0, which gives us the pointer that, hey, we're trying to write to 0 in that case. We've mostly taken a look here at memory-related issue. Let's take a look now at what would happen if the CPU, if there is something wrong happening with the CPU with a divide by 0. So as you hopefully may all know, you cannot divide by 0 mathematically. So whenever you do that inside the kernel, the CPU would throw out an error. Here's a very simple example of code where we have the variable a, the variable b, and we set the variable c to a over b, and we try to print that value. And once we try to run that example, we can see that the kernel crashes with an invalid operator code. So it just says that this is an invalid operation, and the instruction pointer is pointing to div by 0 in its function. The call trace itself is also pretty explanatory, where we can see also that there's something happening on the assembler level, exec invalid operation, and we can see that the call trace points out to our div by 0 init function. Using GDB, we can, as always, look at the backtrace too, where we can see all of that information. But what we can do also is take a look at the values that are set. Here, it's pretty understanding looking at the code, but maybe there's a user input happening that will set the value of b that you didn't know could be 0. GDB would help you see that. So basically just typing print b when you're reaching to the point of the crash, we'll see that, hey, actually this shouldn't happen. We need to debug this. Something funny you could do with GDB also is change on the fly the value of your variables and see that it's actually working. But yeah, GDB here really helps us understanding that one of the values we're reaching out to the point of the crash is wrong. So what's the takeaway here? What do we need to understand? Basically, being able to debug the kernel is crucial, because if we're not able to do so and if we're not able to fix these issues, there can be very big vulnerabilities coming. Say, I've given the example of the use after free, which could allow for remote code execution. All of the examples given are very classic triggers. You can have more complicated examples on your sides when you're actually facing kernel panic. In that case, you can always try to check online if people already had these issues. We've heard a lot about AI during these few days, so AI can be also very helpful in that cases. But overall, using GDB and KASAN is being able to use it is pretty crucial, and it's very powerful tools to do some postmortems and runtime debugging. And of course, the prevention is better than cure, so it's always good to use static analysis, sanitizers, code review, some unit tests, and that kind of stuff. And I've also attached here tracking down and identifying problems, which is part of the Linux kernel users and administrators guide, which has a lot of information about going deeper into kernel crashes and kernel panics and how to report them, and how in production you would need how in production you could collect some of this information. And so that's it. If you're interested, you can take a look at that. And now we'll take a look at command line parameters and its impact on performance. And I will let Hardik talk about that.
Thank you, Thomas. Yeah, so as Thomas mentioned, once we have fixed the kernel, now we might be in a stage where we are seeing performance issues with our system. These performance issues might be coming from different things, and it might be coming from kernel, and there can be multiple factors. So today we are going to look at how command line parameters could impact the performance of your system. So we will start with what are command line parameters. They are basically the text passed to the program during boot or execution. With these parameters, we can configure the system's behavior at runtime. And some common parameter examples are like Linux kernel parameters, like bootloader. Grub is one example. So bootloader is the first program that runs when the system starts up and it loads the kernel. Then we can pass more command line parameters to the kernel. We will take some example in the later slides. And then we can also pass user space application parameters, like if the application allows to use parallelism, we can ask it to use multiple threads. We can also change the cache size that could impact the performance. So why do they matter? So command line parameters can impact multiple things. First is CPU utilization. So these parameters influence how often a CPU is interrupted. So if we enable this parameter no hertz, that will reduce the number of timer interrupts to the idle CPUs. That will save us some power. Second thing here is memory usage. So this parameter sets up huge page table. So using huge page table allows large memory blocks to be allocated, and that will reduce the number of TLB misses that could impact the system performance. So same with the startup time, and then you can command line parameters could also be helpful in debugging. Like you can add more logs to your system, more traces to the kernel logs. So tuning these parameters properly can unlock major performance gain. We can reduce the kernel boot time. We can reduce the memory consumption, increase the throughput. So out of these parameters today, we are going to focus on kernel level parameters. So they can control various aspects of the system, like performance, debugging, security, hardware configuration, and boot timing. So some common examples are log level. We can set different values to the log level parameter, and based on the values, you will see either verbose logs or lesser amount of logs in your dmesg. So another parameter could be console, like if we want to redirect our dmesg logs to the serial console, we can do that. And one kernel level parameter that I have used recently is to block the initialization of certain subsystem. So there might be a case that your one kernel is used for multiple applications, and in one of the applications you don't need a couple of subsystems. So that could, in initializing those subsystems, could impact the boot time, because now the boot time will take more time. But since it's a common kernel, we can't disable those subsystems from the config options. So command line parameters could be helpful for that. So we can use init call restrict, and we can pass whichever subsystem we want to restrict. So today we are going to focus on the security and performance part, and specifically we will look at mitigations. So what are mitigations? So kernel mitigations are the techniques used to protect the system from software and hardware vulnerabilities. So there are different types of mitigations, like memory safety. So the goal here is to protect the usage of uninitialized, stale, or freed memory that could lead to data leaks. The second thing is stack protection. So the goal here is to protect the buffer overflows. So the third thing could be control flow integrity. So it protects the redirection of execution of unintended code. And the last category here is speculative execution. The goal here is to prevent the data leak during speculative execution before instruction validation. So we can disable all of these mitigations with the command line parameter, this mitigation equals to off, but that is not recommended for production, and we will talk in the later slides why. So today we are going to focus on speculative execution. So we will talk about what speculative execution is, how it creates a vulnerability, and how kernel fixes that vulnerability. So one of the most important areas mitigated by Linux kernel is speculative execution. So it is a performance optimization technique where CPU predicts the outcome, and then it executes the predicted path. If the prediction was correct, then the execution continues, and we can save some cycles. And if it is incorrect, then it flushes everything. So this led to speculative execution vulnerability. In attacks like Spectre, an attacker can trick the CPU to execute a speculative path that could lead to data leaks. There could be some malicious data path there. So there are different types of speculative execution vulnerabilities. First one is meltdown. That causes kernel memory to user space by out-of-order execution. The second thing here is Spectre, that exploits branch prediction to access unauthorized memory. And the last one in this list is Red Blood. So it's a return-based attack that bypasses traditional defenses, and it abuses the return instruction speculation. So the Red Blood, it causes more refined classes of attacks like SRSO, that's speculative return stack overflow, that was disclosed in 2023, and today we are going to talk about it. And we will talk how it is mitigated. So before doing that, this is an example from my system, like how command line looks like. So we can read this /proc/command line file, and we have already discussed the highlighted parameters. And you will see that since mitigation off is not present here, so that means mitigations are enabled on my system. And we can read the mitigation status from sysfs. So we can read this file, sys devices system CPU vulnerabilities. And the output will look something like this. So in the later slides, we will go over this output. And today we are going to focus on the mitigation that is highlighted, spec rstack overflow. So what is SRSO vulnerability and how kernel mitigates it? So for SRSO vulnerability, it is related to return stack buffer. It affects the return address prediction used by CPU for performance. So let's first go to the next slide, and then we will come back to this slide. So let's first understand what is RSB, or return stack buffer. It's a critical component in modern CPU microarchitecture design. It speeds up the performance for the function returns. And how it works is whenever a function call is executed, the CPU pushes return address to the memory, plus it pushes a copy to the RSP. So whenever a return command is executed, CPU speculates using the return address from RSP immediately. Meanwhile, the real return address is fetched from the software stack. If the speculation was correct, then great. It's great that we have faster execution. If it was wrong, then it discards the speculative work and use the real address. This speculative return saves hundreds of CPU cycles in case the return address was not present in the stack. Now we will talk about how kernel mitigates it. So the kernel uses two functions, the function SRSO untrain return alias and SRSO safe return alias. These are specifically designed to mitigate speculative execution attack. And with this mitigation, before returning from a function, kernel calls this SRSO untrain return alias. It pushes multiple safe address to the RSP. And when return command executes, CPU speculates and gets the return address from the RSP. And those return address points the CPU to go to this SRSO safe return alias function. And in the meanwhile, actual return address is fetched from the memory. And once CPU gets that, it starts executing the actual address. So the security benefits here are like, even if speculation happens, it's routed to a non-malicious, non-leaking location. Real control flow is preserved. Speculation is discarded once we get the correct address. So this example shows the vulnerable versus the mitigate path workflow. So with vulnerable path, function executes with normal return. It uses the CPU prediction. It gets the address from RSB that is poisoned by the attacker. And then it speculative executes to the wrong target. It jumps to the wrong target. That could lead to data leaks. With mitigated path, the function executes. CPU predicts, it goes to the RSP. The RSP's addresses were already flushed, and it was already untrained, and the safe addresses were pushed to it by SRSO untrained return alias function, and then it goes to the SRSO safe return alias. So this is the sysfs output. We can see multiple outputs from there. So like for your mitigation, if it says it's mitigation safe ret no microcode, that means software mitigation is in place. If it says it's vulnerable, but it says safe return and no microcode, that means it's partially partially protected. If it says it's vulnerable, no microcode, then it's fully vulnerable. But if it says mitigation, red blood plus SRSO mitigation, that means your system is fully protected. So now, why we are talking to this regarding these mitigations? Because in our work a couple of months back, we were working on performance differences between 5.15 and 6.6 kernel running on the same hardware. And there we saw there was a 12% performance difference between those two kernels. And like ideally, when we work on two major kernel versions, we expect performance differences. We expect that the newer kernels performs better. But this performance number is pretty huge. So there could be multiple factors, like hardware was same, so there could be something in the configs or something in the source code. So we started to bisect the source code, and then we found out there's a new commit introduced in 6.4 for this RStack overflow mitigation that was causing this 12% performance difference. And if you open this link, even the author has mentioned that we need this protection for the production systems, but it will give you some performance differences. So in conclusion, we can disable the mitigations, but there are pros and cons. The pros, there are significant performance boost in syscall heavy IO-bound workloads. It reduces noise in benchmarking, like while benchmarking, we don't need to enable these mitigations. And the cons are, if we disable these mitigations, then the system is vulnerable to kernel memory leaks, side channel attacks. So that's all from my side, and thank you for listening. Please let us know if there are questions. Yeah?
Okay, so first of all, for the first speaker, if you are talking about recursion of kernel, if you try to use this, your colleague will beat you. So never use recursion in kernel because you have only 1 kilobyte stack. And I would like to see something like more real-life example, because you can take any bug in the kernel and show that you can use this to solve this problem. Second, if you're talking about use after free, usually it's something like race condition, and GDB completely useless in this case. You was very lucky if you can catch this, because if you have rest condition, GDB change your latencies, and you're simply losing this issue. So again, GDB, I don't know, I never use the GDB for the whole my career, because in 99%, it's my opinion, in 99% of cases, you don't need a GDB at all. And if, for example, customer complain to me that I have corruption kernel, I cannot use GDB because I can ask something like favor, give me some more details and so on. This is my question. When I receive a kernel corruption from end user, it can be an open source MLRS discussion, or it can be something like a real customer something like complaining to me. Sometimes, very frequently, I need to have something like more deeper discussion with customer. What is happening around, because what I see is called trace, it's not informative. So what can we add? Maybe we can add some additional details to have something like more easy way to track the bug and to find the solution. What's your opinion?
Yeah, absolutely. So just to give a small summary of what has been said, basically what has been said is, first and foremost, the example of Stack Overflow is not something that really is in a use case in a kernel, because it's something that is being consistently avoided, and that's absolutely true. The second discussion point was the idea that using use after free is often something due to race conditions, and these race conditions cannot be followed through using GDB, which is completely right. In any case, this was mostly meant to be an introduction, so we went over through all of the debugging techniques that we had, so I didn't want it to skip GDB in all cases. And this is completely right about the issues of Stack Overflow. In any case, yeah, these kind of issues are pretty common and pretty standard and pretty simple. The goal was to give tools. What I was saying is that the first idea that you need to go through is that if you hit a memory-related issue, enabling KASAN, it's not something that everybody thinks about, so enabling KASAN would be a very good first step of going deeper into it. Using GDB also, if you don't know exactly what happens, could also help finding where the issue is coming from. Not if it's a race condition for sure, but who knows if we end up in that case. what I tend to give, like what my first point of opinion is to look at why the issue is happening, like basically what the kernel crash basically says at the beginning. There are so many different crashes that could be happening that it was not possible to cover all of them in the slides and everything. So the goal here was mostly to give out the good practices in knowing what to do. So of course, there are some issues that could be happening. I cannot give examples of what you could do in all of them. What I wanted to do was mostly give good practices. So what I would recommend is taking a look at the kernel dump logs if all else fails, and try to see if anybody has replicated that issue or had something related, or if it's something that's upstream. You could also talk with the community upstream up there. And as I've said in the end of my slides at the takeaway, that today there is so many tools that you can use to help yourself also. So with AI agents, but also just Googling it. So yeah, that's like the steps I would go through if I encounter any issues, any kernel panics.
But could we add something more, kernel trace, maybe some more details, what's your opinion?
Well, there's a lot of different debugging tools and that kind of stuff. We mostly wanted to cover KASAN and GDB. If you know any more, or if there are any more, feel free to share. But in any case, what you can do also is add debugging information about the kernel. So Hardik was talking about the log levels. There are some prints that would print out only if it's debugged. So having them enabled could give out more information about the log, about what's happening inside the kernel and everything. It really depends on where you're looking for and what you're looking for.